There are three types of exceptions to the octet rule. I will list them here and then go over each one in more detail. Odd electron molecules, as the name implies, have an odd number of valence electrons in the shared pot. There is going to be no way for all atoms to have 8 electrons around them. The central atom usually ends up with 7 instead of 8. Electron-deficient molecules have a central atom with fewer than 8 electrons. This occurs when the central atom is in group 2A or 3A. Hypervalent means that the central atom has more than 8 electrons around it. Hyper means above, and valent refers to valence electrons, so they have more than is usually needed. This can occur when the central atom is from period 3 or below. Let's start with our first exception, odd electron molecules. You might hear the term free radicals being thrown around in the media. They're the same thing as odd electron molecules. They will end up with an unpaired electron, which is very reactive. As you are drawing Lewis structures for odd electron molecules, follow your same 5 steps, and you should end up with the correct structure. Let's look at an example. This time we are doing the neutral NO molecule rather than the NO plus 1 ion. Step 1. Count the valence electrons. Nitrogen is 5 and oxygen is 6, so there is a total of 11. We don't add or subtract any because it is not an ion. Step 2. Draw the stick figure by connecting the nitrogen to the oxygen with a single bond. Step 3. Complete the octets of the terminal atoms. It is going to be really important to put the electrons on the more electronegative atom. Remember, if it's more electronegative, it wants electrons more. In this case, we give 6 more electrons to oxygen. Step 4. Place any remaining electrons on the central, least electronegative atom. We started with 11. We used 2 making the double bond and 6 making the lone pairs on oxygen, so that leaves 3 left over to put on the nitrogen. We put 1 pair and 1 single dot. Step 5. Check the central atom for an octet and make double or triple bonds if necessary. The nitrogen has only 5 electrons around it. If we borrow 2 electrons from oxygen, that would give it 7, and we end up with a double bond. The oxygen still has 8, but the nitrogen has 7. We do not want to borrow a second pair from the oxygen because that would give nitrogen 9, which is more than an octet. Nitrogen is not in period 3 or below, which means it only has access to s and p orbitals and can therefore not handle any more than 8. Our second exception is electron-deficient molecules. You will be looking for the central atom to be in group 2A or 3A. When that's the case, the central atom will have less than an octet. This is often because there are just not enough electrons in the shared pot to go around. People didn't bring enough food to the potluck. For example, in BeH2, beryllium has 2 valence electrons because it's in group 2A, and hydrogen has 1 valence electron. So there are a total of 4 electrons in the shared pot. After making the 2 single bonds for the stick figure, there are none left over to make lone pairs. The beryllium is left with only 4 electrons around it. Similarly, in BH3, boron has 3 valence electrons, and there are 3 electrons from the hydrogens, so there are 6 electrons in the pot. After using the 6 electrons making the single bonds, there are none left to put as lone pairs on the boron. It is left with only 6 electrons around it. In both of these molecules, step 5 is not an option because there are no lone pairs to borrow from hydrogen. Some molecules, like BF3, could be drawn 2 different ways. It could be drawn with a double bond to one of the fluorines, which would complete the octet of the boron, or it could be drawn with only single bonds, making the boron electron deficient. Experimental evidence, such as measurement of bond length, indicates that the structure with single bonds represents the molecule better than the structure with the double bond. As you approach Lewis structure problems in the class, the only time you will not follow all 5 steps is when the molecule has a central atom from group 2A or 3A. When that is the case, stop before step number 5 and do not make any double or triple bonds. Electron-deficient molecules can do some cool reactions, including forming a coordinate covalent bond. They can react with a molecule like ammonia that has a lone pair on the central atom. The lone pair fills in the empty spot on the boron and makes a bond. Normally, a bond is formed by 1 electron from one atom and 1 electron from the other atom. This is different because both electrons come from only one of the atoms in the bond. Once the bond is formed, it's no different than any other single bond. The difference is in the origin of the bond. Which of the following is electron deficient? Is it A, CF4, B, PF5, C, BH3, or D, NO3-2? The correct answer is C, BH3. First of all, we just went over BH3 as an example of an electron-deficient molecule. What you are looking for is for the central atom to be from group 2A or 3A. The central atom is often listed first, so that can help you figure it out. The third exception to the octet rule is hypervalent molecules. Hypervalent molecules have a central atom with more than 8 electrons around it. These can occur when the central atom is in period 3 or below, because that atom has access to d orbitals. You will still follow your 5 steps of drawing Lewis structures to find out if the central atom is hypervalent or not. Just looking at the identity of the central atom is not enough to tell you that it will be hypervalent, only that it can be hypervalent. For some molecules, it will be easy to figure out if they are hypervalent. If there are more than 4 bonds to the central atom, then there must be more than 8 electrons around it, and therefore it must be hypervalent. For example, PCl5 has phosphorus bonded to 5 fluorines, so the phosphorus must have at least 10 electrons around it. SF6 has sulfur bonded to 6 fluorines, so the sulfur must have at least 12 electrons around it. For other molecules, drawing the Lewis structure will be the only way to find out that it is hypervalent. That is because there can be lone pairs on the central atom, which are not apparent from the molecular formula alone. IF5 and XEF4 are examples of hypervalent molecules that contain lone pairs on the central atom. Both molecules have 12 electrons on the central atom. Let's go through drawing the Lewis structure for XEF4. Step 1. Count the valence electrons. Xenon is in group 8A, so it has 8 valence electrons. The 4 fluorines give us a total of 28 electrons, since fluorine is in group 7A. Total, it has 36 valence electrons. Step 2. Draw the stick figure. It has fluorines attached to a central xenon atom with single bonds. A lot of students are tempted to stop here, especially when they are running short of time on an exam. Do not do it! You must do all 5 steps. Step 3. Complete the octets of the terminal atoms. Each fluorine gets 6 more electrons. Step 4. Place any remaining electrons on the central atom. This step is really, really important. We started with 36 electrons. We used 8 making the single bonds and another 24 making the lone pairs on the fluorines. That still leaves 4 electrons left over. Any leftover electrons must go on the central atom, so we place the 4 electrons in pairs on the xenon. It ends up with a total of 12 electrons on the central atom. Step 5 would be checking to make sure the xenon has a full octet. It actually has more than an octet, but that's fine since xenon is in the 3rd row or lower on the periodic table. Which of the following is hypervalent? Is it A, CO2, B, PF6-1, C, SO4-2, or D, H2O? The correct answer is B, PF6-1. The central phosphorus atom is surrounded by 6 fluorines. Those 6 bonds make it automatically hypervalent. As you complete homework and exam problems, you will want to check for the ones that are automatically hypervalent due to the number of bonds. If there aren't any, then you would need to draw the Lewis structures of all the molecules in the answer choices.